and I'm very happy to get the chance to present the idea and some results of our recent technical brief of our publication. I've heard that there are many participants from many countries all over Europe or all over the world, and yeah, already now at the beginning I want to say thank you for your interest, and I'm happy and also a bit excited to talk here for the first time. Also for me it's the first webinar that I give. For this webinar I have chosen where is it? Yeah, it works. I've chosen the title, the more entertaining title, Tubulin or not Tubulin, that is the question, a better loading control for Western blots. And this Shakespearean idea came from my colleague Thomas Schulenborg, who is also one of the co-authors for the publication in Proteomics, which came out at the beginning of this year. We have chosen the more factual or objective title, Epicaquinone staining, a powerful loading control for Western blots. And yeah, the idea of this paper addresses something that is very often seen in life science publications, and something that might be familiar to all of you, to the listeners. I have prepared here a scenario, a schematical scenario, in order to not criticize one particular publication. So what is seen here, you see here a control situation, and yeah, the two drugs, application of two drugs, and what is tested here is antibody A, antibody B, and you see that antibody A and B yeah, are a bit reduced upon the application of drug 1 and drug 2 respectively. And what is often seen at the bottom panel in such figures is something like this. This is a housekeeping protein, generally here tubulin or actin is often seen, and the aim is to have a loading control. Yeah, what is this? Why is it important to use a loading control? Imagine this situation. Your signals are weaker upon application of drug 1, and there are two scenarios now possible. Either there is really less protein A after drug 1 application, or another possibility, maybe you have loaded, because of any reason, less total protein on the gel in these two lanes. So it is necessary to have a loading control, and many groups use a housekeeping protein there, and yeah, and now you assume that drug 1 has no impact on this housekeeping protein, on tubulin or actin. Generally this is not tested, this assumption, but if this assumption is true, then indeed there's less protein A after drug 1 application. But the problem here is that when you use housekeeping proteins as a loading control, your interpretation is always based on this assumption. It could still be that you have loaded less total protein here, but drug 1 has an impact, an enhancing impact on the cytoskeleton, on tubulin or actin. This is yeah, usually never checked. So taking a single protein is not always representative for the total protein amount. And I would like to show this by an analogy of the Soccer World Championships of this year. And here you see the 4 winning teams, the 4 best teams of the games, and the question, how many goals did the soccer teams make in Brazil, or which team made the most goals? And to answer this, you can look up in some tables. You see that, I call it here the analogy, the total goal count, that Germany was the top scorer. They made 18 goals. The second best were the Netherlands with 15, and so on, 11 and 8 for Brazil and Argentina. And now assume that we would not know this total goal count. Then we need some representative, let's call it protein, to assess the total goal count. And in soccer team we don't have a housekeeping protein, but what we have is a goalkeeping protein. For example, Neuer and the German team, or other other guys in the other teams. And you see no one of these goalkeeping proteins scored, no one made a goal. So this would be no good idea. The goalkeeping protein is no representative way to assess the total goal count. Now I checked other players, and I found I took the key player, or called it here the key protein, and this is a better one, a better quantification method, because let's take the example here. The key protein, key player of the German team was is Thomas Müller. He made 5 goals in Brazil, and thereby he made more goals than his 3 colleagues of the other 4 best teams, and thereby he is representative. He made the most goals in Germany, made the most goals, but Robben, the key player, key protein of the Netherlands, made only 3, Brazil and Argentine 2. So if you want to state it like this, Neymar and Messi were a bit overrepresented, which means altogether that to take this key protein is a bit closer to assess the total goal count. However, it is still not the best. So again, one single player or one single protein might not be representative for the whole team or for the total protein that is loaded on the shell. So the best would really be to count the goals, so to have a way to count the goals, or in the language of protein science, to somehow stain the total protein. If you stain the total protein, this is then representative, or at least more representative. So this idea to take the total protein as a loading control does not come from our group. It's older. It's also not invented by those two, but they had also an idea 3 years ago. I think it was in 2011, a publication in Journal of Proteome Research. And these 2 authors suggested Coomassie staining as a good loading control. So what they did is they used GAPDH and compared it to Coomassie. They saw that GAPDH had somehow a ceiling effect, so they increased the protein amount, but the signal didn't increase, which was not the case with Coomassie. So that was one reason why they concluded that Coomassie is a better loading control than housekeeping proteins. They are right, that's true, but there's one crux, one disadvantage with using Coomassie staining, and this is that it's incompatible with subsequent immunostaining. Now you might ask, is this important to be compatible with subsequent immunostaining? And yes, it is, because when you do it at the very end, so when you use Coomassie staining, you have to do your loading control at the very end, after you have done all your immunostainings. Then you see maybe at the very end that some of the blots didn't work, either the Coomassie staining didn't work, then you have no control, or you see something like this, that there is a part of the blot, maybe even a part where you expected your signal, which did not perform very well. Maybe there was an air bubble or something like this, and then if your signal would be there, then you cannot use it. And if you see this at the very early stage, maybe directly after the protein transfer, directly after the blotting, it would save money and time. So we used for an alternative and found some staining methods which are based on epicaquinone. What is epicaquinone? Here you see the chemical structure, how it looks like. It was described a bit more than 10 years ago by Bell and Caruso, and it is described as a fluorescent compound from the fungus Epicoccum nigrum. So it's a natural compound, and in the publication and also in the talk now, I do not want to use this long phrase, but that's important for the understanding of the slides. When you see here these E-tops, this means, but I also will say the name, it means epicaquinone-based total protein staining. And 2 further variants of this abbreviation is that there is a natural variant, and we use the N here, and there is a synthetically modified variant, so we use the S for the synthetic. And we we had some open questions in our lab that we wanted to address in our lab, and this is the calibration curve. What is the calibration curve? And connected to this, the sensitivity of this epicaquinone staining. What about biological variation, technical variation? I will explain what I mean with this. And what about the compatibility with immunostaining? Also, this has, to our knowledge, not been addressed so far. So, in the publication, and now in the next 3 slides, I will address these points together. The first one's calibration curve, the variation, and the compatibility with immunostaining. And yeah, so the first point, the first thing that we addressed was the calibration curve and the sensitivity. And to do so, we performed several blots, blood membranes, gels, where we loaded different amounts of proteins, of a total protein mix, a homogenate of tissue. And here you see, for example, we started with the biggest amount, 30 microgram, and went down to loading amounts where none of the staining variants were able to stain something, to label something. And you see that the ETOPs, the epicaquinone-based stainings, stained down to 0.1 microgram of total protein staining, and none of the other tested staining variants was able to stain down to this level. This was not only seen in this n=1 approach. We did it several times, of course, and made a graph and made statistics. And also over these several plots, it became apparent that you see it here, that the dynamic range of the epicaquinone-based stainings is broader. Here in the light green is broader in terms of the protein amount that is loaded compared to the other stainings. The other stainings decline faster and then disappear earlier. Earlier means at protein amounts in this range between 0.1 and 1 microgram total protein. It disappears here somewhere in the background. So that is a first advantage of the epicaquinone-based total protein stainings compared to other total protein stainings and to housekeeping antibody stainings. And then what you see more often in publications is not the loading of a total protein staining, maybe this is closer to what is used in biology, but to find a kind of absolute minimum. It is more often seen, and also we used that here, that we loaded only one protein type. Here in this case we loaded beta-lactoglobulin in different amounts down to 0.1 nanogram, and the epicaquinone-based stainings were able to stain down to 1 nanogram in both cases. So we didn't see a difference. Also here in the B1 panel we didn't see difference between the synthetic and natural variant. Also here we didn't see differences, but we saw a difference to cycloruby, for example, which only had a sensitivity down to 30 or 10 nanogram. Then in the next, the bottom line or take-home message of this slide was that the epicaquinone-based staining is more sensitive than the other tested staining variants, and thus has a broader dynamic range. In the next experiment, we addressed the biological and technical variation. With what do we mean here with biological variance? We mean here, in this case, that we check the variance across different organs, even different organs of the same animal. Here we compare the signal intensity of total protein staining and of the two housekeeping proteins of the same animal. Animal 1, we compare heart, liver, lung, and kidney. And you see already by eye that tubulin and GAPDH has a relative strong variance, because the tubulin signal in heart and in liver is stronger, significantly stronger than in kidney, for example. So this clearly speaks against the general assumption that housekeeping proteins are equally expressed. And the same for GAPDH, and this means when you check now the variance across these organs. So we took here the coefficient of variation, to press it in a number somehow, this variance. We saw that this variation across the organs for the single proteins, for the immunostainings, is strongly higher compared to the total protein staining. You might say now that organs are very different from each other and that this situation is kind of arbitrary. So what we did is to address not different organs but tissues which are very similar to each other. And these were regions of the brain, and not only different brain regions, even 3 regions. You needn't know here what the abbreviations stand for, but these are 3 regions of the auditory brain stem, and so they are quite similar to each other. And still, although they are similar to each other, you still see that there's a variance when you look at the single protein players in these regions. The tubulin, for example, is strongly higher than the other regions, again demonstrating that housekeeping proteins are not always equally expressed. But to avoid this problems of the housekeeping proteins, you can take total protein staining, and here again the variance is strongly reduced compared to the housekeeping proteins. What about the technical variance? The technical variance means that we loaded here 12 times the same sample on one shell and then several other shells, and then again measured the coefficient of variation, and once more we found that this coefficient of variation for the epicaquinone based total protein staining is smaller than for the housekeeping proteins. So this means altogether that the epicaquinone based total protein staining showed the lowest biological variance and also the lowest technical variance compared to the generally used housekeeping proteins. And then in a last experiment of our publication, we addressed the impact of this total epicaquinone based total protein staining on a subsequent immunolabeling. And what we did here is that we performed several Western blots and stained them with tubulin, for example, tubulin antibody and the GAPDH antibody, and we treated all these Western blots exactly the same, except of one thing. Half of them were before antibody incubation were stained with the epicaquinone staining, and the other half were not. And also by eye, you see no obvious difference between the ones where epicaquinone was applied prior to immunostaining or not. And also when you quantify this, you see that the impact is measured. Is it after the epicaquinone staining? Is it maybe even stronger or less intensive than without the staining? But we have neither enhancing effect nor a reducing effect. In none of these cases there is a significant difference. So also when you plot the normalized signal intensities against the volumes that you have loaded, the amounts in nanogram, you get these calibration curves here, and also these calibration curves do not show significant differences. So this means that the epicaquinone based total protein staining has no impact on the subsequent immunostaining. So then one of the reviewers, that was quite a very good point of one of the reviewers, we were very appreciated this comment, because he said, yeah, you have nicely shown in your publication that this epicaquinone based staining is better than other loading controls, but what about the costs? But because he thought fluorescence staining could be more expensive, and so it was a quite good idea to compare the costs. And I did this. You know, prices can change very fast, so this was the situation when we bought the material 1 to 2 years ago. I don't know if this is still the the case. So what is shown here are the prices for the amounts that can be bought, but then I calculated how much do we need and how much would it or does it cost when you stain one membrane. So this is the one that you can compare. You have one base, you can compare the different staining variants better to each other, and you see that the fluorescence stainings are not that expensive. So it a bit depends on where you buy the staining variants. By the way, here you also see the commercial names. In the paper up to now in the talk only used the scientific names, but here you see the commercial names as well. And yes, they were quite low. One was lower, and this is Coomassie. Coomassie was the cheapest variant, only 9 cents per membrane, the cost for staining. Yeah, but Coomassie has this disadvantage that it's not compatible with antibody stainings thereafter. So these ones, the epicaquinone total proteins and the Coomassie variants, are for the concerning the price, are the best ones, if you want. So these were the cheapest ones, cheaper than Cyperubi, or also cheaper than the antibody stainings against Tubulin or GAPDH. But I don't want to keep secret that you of course need a fluorescence scanner. This is not included here. So, but this is also true for the Western blotting. So when you do housekeeping protein immunostainings, then you need some chemiluminescence imager. So this is not included here. So for the epicaquinone staining, you need a scanner in your group or neighbor group or somewhere in your institute. But I think that's meanwhile often the case that there is some in the department. So before I summarize my points, I would like to give you an overview. Maybe you ask now, you wonder how fast is the staining protocol. Maybe you up to now did only the housekeeping proteins as a loading control, and how fast is it? Is this a disadvantage maybe? You see here I took the I just looked up at the SERVA homepage and took the SERVA purple variant and looked what times. This is the newest one. That's why I've chosen this and the times that are recommended here. And you see that there are 6 steps. And the first step is just the washing step, some incubation step, staining buffer. Then this is the actual staining step, the longest one, with 15 to 30 minutes. Then an acidification buffer. By the way, the buffers are quite simple, so they need not much time, only 1 to 2 ingredients per buffer. Then there's a methanol washing step and try the blood membrane before you then can image. Altogether, this staining protocol lasts about 1 hour plus minus some minutes. So also this is no disadvantage, because when you use immunostainings with housekeeping proteins, then you know that the traditional variant, already alone the primary antibody incubation lasts 2 hours. So also this is no disadvantage. I would like to sum up the points about the epicaquinone stained base total protein staining, which is more sensitive and has a broader dynamic range than the other tested stainings. Further, it has a smaller biological and technical variance than the traditionally used housekeeping proteins. It has no impact on subsequent immunostainings, which is important to do it in a very early step. You save money and save time if you not need to wait until you put all your antibodies on the plot to find out if they were loaded well and equally. And it's also cheaper than most of the other tested staining variants. So as a conclusion, I would really recommend to use total protein staining instead of immunostainings for loading controls. Of course, I do not say buy now the SERVA purple. This is the job of Mark. But if you now do immunostaining and you want to switch then we have shown that the epicaquinone-based total protein staining is better than other total protein stainings. Okay, so then hopefully in future publications, to come back to this slide, future publications hopefully look somehow like this. That you don't have a loading control which is a housekeeping protein, but which is a total protein staining. Yeah, with this I've shown you the idea and the results of this publication, and I thank you all for listening. I thank you for your interest, and I also thank Mark for inviting me to this guest talk, and yes, I'm open for some questions and give the word back to Mark.